So let's go a little bit more into just the appearance of Jupiter, the atmosphere, um, and of course the density. All right. So once again, this is the density of Jupiter. You get the mass, of course, by having satellites, the moons, I should say, which are also known as satellites, orbiting Jupiter, and we can measure the period. Um, and of course, we measure the distance between the satellite and Jupiter, and that's how you get D. And the period is actually the easiest thing to measure. So when we do that, and we use the size of Jupiter, the angular size as seen from Earth, you can get what the radius of Jupiter is, so you can figure out the volume. And then, of course, you take the mass divided by the volume. Volume of any sphere is 4 pi over 3 times the radius cubed. And we do the rate, you got to change the radius into centimeters, and then you cube it. The mass has to be in grams. All right, so it's as I said before, about 1.3 grams per cubic centimeter, much less dense than the terrestrial worlds, because of course they're made mostly of hydrogen and helium. But there's stuff inside of Jupiter that's way more dense than even than this. Remember, this value 5.5 is the average density of the Earth. There's stuff inside of the Earth that's much more dense, more like closer to 8 grams per cubic centimeter, because that it's iron and nickel, which has a density much higher. Jupiter, of course, has an interior that has a higher density, and in fact, it's a much higher density than we find on the Earth. All right, so let's go through. Now we've sent satellites. As I said before, the Galileo satellites orbited Jupiter for a number of years. As I'm making this video, the Juno satellite is currently in orbit around, and we'll have a lot more to say about this. But the Juno satellite, it's kind of interesting. What it does, it's in a very, very elliptical orbit. So what it does is, Juno, we wanted to be able to get images of the north and south poles, and so what it does is it orbits, like around, from north to south. So it orbits in this manner, but it orbits in a very, very elliptical orbit. At any rate, it gives us all sorts of information. So one of the things that Juno does, the Juno spacecraft, is that it measures the difference in gravitation at different locations around Jupiter. And the reason for that is that can tell you about what is happening in the interior, right? So from the information that we have so far, the Juno spacecraft tells us that there is perhaps a rocky, more and more it's looking like there is some kind of rocky material at the very center. But this is many, many times the mass of the Earth, right? I mean, Jupiter's already way bigger than the Earth as it is, so it's not surprising that there's going to be stuff in there. But as far as so if we just concentrate on the hydrogen, I mean, the other stuff that makes up the colors is methane and ammonia, and some water vapor as well. So the white area here, these are called the zones. The darker area are the bands. We'll get into that in just a minute. But so this is one of the things that Juno found, is that in our, well, actually the Galileo spacecraft was one of the first ones to determine this, is that deep within Jupiter, so as you go further and further into Jupiter, of course the density increases. Just like going underneath the ocean, right? The density, the pressure increases as you go further and further, and so as the pressure increases, into greater and greater amounts, and we can actually uh, reproduce some of this in labs, where the pressure gets so great that the hydrogen will actually turn into a metallic liquid. And if the hydrogen is acting like a liquid, that means it's spinning around. And so Jupiter, of course, has this incredibly strong magnetic field, and that comes from the liquid hydrogen. Right? Hydrogen is acting like a metal in this particular case. If you never notice on the periodic table, hydrogen is on the left-hand side. So sometimes hydrogen acts like a metal, sometimes it acts like a non-metal, but in this particular case, it's acting like a metal, and so you get these huge currents inside of Jupiter, and it's producing magnetic fields that are, I think sometimes they're more than like 20,000 times the strength of the Earth's magnetic field, just to give you an example. All right, so it turns to liquid, and then even as you go deeper and deeper, of course, because we know the mass, and so we use this the physics of what's sometimes called hydrodynamics. We can use this physics to figure out what the density would be really close to the center, and the density would be just tremendous, like many times the density of just normal iron, right? And yet the overall density, because it's such a big planet, the overall density is still about 1.3. Right? So that's sometimes that's called the bulk density. Just to let you know. All right, so let's see what else. All right, so I'll talk more about the Juno spacecraft later on. So you get the metallic hydrogen, and there's actually we think that there's solid, so hydrogen in a solid form. At least there's some models that predict that. And what we generally do with these kind of things is we program the equations of physics into supercomputers, and then feed it as much information as we can from various sources, like the Juno spacecraft, even going back to the Galileo spacecraft, and then we see what are the results of these supercomputers. What do they predict? What would be the density at different distances from the center? All right, so let's see. So Juno, this is in the visible part of the spectrum. So you can see. Let's take a look at it from 2009. You see the white parts are the zones. By the way, I know I said that already, but the darker part are the bands. Right. So there's the zones and the bands. Notice from as time goes on, they visibly change. Right. They definitely change over time. And you can see that in the infrared as well, that these zones and bands are undergoing changes. Some of that is due to the sun, due to the slightly different distances from the sun. Some of it is some kind of chemical reactions that are going on in the atmosphere that maybe we're still trying to understand what's going on in the atmospheres of these gas giants. The atmosphere, just like our atmosphere, for example, the atmosphere is a very complicated thing to make predictions and so forth. And for the exact same reason that the weather is really hard to predict, right? All right, so using, as I mentioned before, the physics of known as hydrodynamics, it's known by other names too, thermodynamics as well. Anyhow, we estimate that the core temperature is about 30,000 Kelvin. And one of the things, okay, so one of the very first things that we figured out, and this was a long time ago that we figured this out. You can, for example, measure how much, um, how much heat is received by Jupiter from the sun, right? And so we know that we know the exact amount of heat that's coming from the sun, and it decreases as the square of the distance, right? That's the inverse square law. Um, and that we get a certain amount of heat here on Earth, and you get even less heat on Jupiter. But the thing about Jupiter is, even if you look at the amount of heat that the sun is giving to Jupiter. Jupiter gives back more heat than it receives from the sun. All right, so let me repeat that because it's really important, and we're going to find this in some of the other gas giants. So Jupiter gives off more heat than it receives from the sun. Okay, so there's something going on internally inside of Jupiter. That's the first thing. And like I said, we've known this, I think, since the 1970s. We've actually known about this excess heat that comes from Jupiter. But just to let you know, we also know that there's this excess heat that comes from Saturn as well. But that excess heat, we think, is arriving from Saturn for a slightly different reason. So we think that Jupiter is still giving off the heat of formation, that it formed by materials crashing into each other and forming these little planetesimals, and then that stuff started growing, and then it started feeding on the original gas material that made up the solar nebula. And as Jupiter got bigger and bigger, the interior of it got hotter and hotter. And so what it's doing now is it's releasing that heat out into space. And so that there's more heat coming off of Jupiter than is going into Jupiter from the sun. All right. So yeah, one of the things that might be happening is that gravitational energy. So if Jupiter is shrinking just by a small amount, it'll give off heat because the gravitational energy is converted into heat. All right. So that's all right. So here are the zones. These are the white areas. Notice the zones and the bands alternate in the direction that they travel. The zones in some people call them bands. Some people call them belts. So the bands and the belts, it means the same thing. All right. So the darker regions, so this picture is calling it the belts. I think I called them bands. At any rate, the zones are going in one direction. The belts, I'll use the terminology that's in the picture right here. The belts are going in the opposite direction. That's actually from convection, just to let you know. All right, so the clouds appear to be particles of water, ice, and ammonia compounds. The brighter colors may come from complex organic molecules, as it says. We really don't understand all the coloration of Jupiter. There might be some sulfur and phosphorus involved as well. So now it's hard to tell how fast Jupiter is rotating, and we found that it's a very difficult idea because remember, it's not a solid, right? So it doesn't rotate around as a solid. But if you look at the equatorial bulge, right, because it's spinning around, it bulges out a little bit at the center. And so if you watch the center, and there's certain formations that occur on the center, and you watch it over time, it takes roughly 10 hours for Jupiter to go all the way around, or to spin once around it on its axis from the center. Of course, it takes less time when you get towards the poles, but that's a different. That's just because it's not a solid. All right, so